Okay, so after up to this point, you have a set of solutions so far. N is the size of population that you keep, a number of solutions in our hands. And K is the size of offsprings. Select two parent solutions, make crossover, perform mutation, and do the repair, and you finally have one offspring. You have one child. And after performing this process k times, and you have k numbers of new solutions. And then you want to substitute a certain part of n with k. Okay. So we need to create a feedback system. We have right now we have n solutions, and the next time we still have the n solutions. But here we want to add k new solutions, and we want to get rid of minus k solutions. And how to perform this substitution? First of all, k divided by n is being called generation gap. So if generation gap becomes large, means that we are replacing almost all the population. If k divided by n equals 1, it means that k and 1 is almost equal, right? Then it means that we are replacing almost most of the population. It's being called generational GA. It's very dynamic change because you just remove all the parents and you just put all the children, and you just remove all the children and you just put all the grandchildren. It's very dynamic society. It's very dynamic population, very changing. However, because the generation changes is pretty big, there is a very slow convergence, very slow approach to the optimum. Of course, this optimum can be local or global. That's being up to how this k is being created. However, it's going to be very slow approach to the whether it is either local optimum or global optimum. To the optimum is going to be slow. If the k divided by n is going to be very small, it's going to be just replacing just one or two few solutions of the population. It's being called steady state genetic algorithm. It's very steady society because we have all the parents and we just remove one parent and put one child there. So it's going to be very steady. But it's going to be very fast to the optimum. Okay. So that's how to choose k values out of from n. And here, this deciding k is now done. Who to replace? How to fix k to be removed from the n number of solutions? Just removing inferior solutions, replacing the bottom k solutions with the new ones? It's a fast convergence, going fast to the optimum, However, just removing inferior solutions make your solution heuristic work? Of course not. You want to keep some inferior solutions. Because of that, you want to have some diversity. Just replacing, substituting inferior solutions with the new offsprings is not going to be that nice approach. On the other hand, just removing the parents, so we have these offsprings and we have these selected parents. Because we are going to put that offspring, we are going to remove all the parents coming from contributed to this offspring. Well, it can be, that's one approach. It can be but replacing the worst parent solution with the new one, well, it might add up some bigger diversity, but still it might have some slow convergence. So it has a different problem. So these are actually your choice. There's someone who runs the genetic algorithm. So you have to experiment a lot to find a nice replace approach, to find a nice K, and to find nice crossover scheme, and to find nice selection scheme, and so forth. Okay, so genetic algorithm is structured in this way. We have genetic algorithm, and we have one big method called perform evolution. You want to create a initial solutions with random approach. This is going to be the random. After that, you want to perform a number of iterations. And you want to find the parents here. And this is K, right? Number of offsprings is K. And you want to select parents. You want to perform the crossover. You want to perform the mutation. And you want to create this K number of new solutions, offspring. And then you want to substitute it with the previous population, with that offspring. After running through the number of iterations, you want to find the most fittest solution, and you are going to return it. So fix the number of iterations, or stop when no more diversities, or stop when reaching a plateau, or stop with time. You have diverse options for the number of iteration selections. You want to have a large population, more diversity, slow convergence, small population, and less diversity, and faster convergence. Usually 20 or 50 solutions. And you want to have a uniform random or just shuffling. There are various types of creating a new initial populations. Okay, so these are the things that I didn't cover, but I believe that you can just program it for these implementations. And we are going to see that in the offline classroom. And other heuristic-based optimization, actually there are many. Okay, so for example, particle swarm optimizations, like this. This is also called ant colony. And we have simulated annealing like this. And we have table searches like this. And I don't want to cover these things, but I'd like to say this thing here in this slide set. Most strategies are the imitation of Mother Nature. Particle swarm, simulated annealing, genetic algorithm, these are the imitations of our Mother Nature. Also, our society, for example, table search. And to have a better heuristics and to find a new heuristics algorithm, you have to appreciate your surroundings and see the deeper insight to discover the new algorithms. Okay, so even though we are dealing with the optimization, actually they are coming from our society and our nature. You want to understand it, and then actually they might give you some insights into the problem at hand. Okay, so further reading is here. This is Korean book. Actually, even though Korean book, this professor, Professor Byung-Ro Moon at Seoul National University is very well known for the genetic algorithm, and this is a great book. So if you are really interested in, please visit my lab so that you can read it. Otherwise, this is also another great book so that you can read it. We are going to do a hands-on exercise on the genetic algorithm in the classroom. And so we didn't have any programming, typing in instructions in this slide set. Isn't that great? Okay. I'm gonna see you in the classroom. Goodbye.